Hi, my name is Koen Verhagen, and I will talk to you about the CDM robustness of Sofics SCR-based ESD solutions implemented in FinFET and FDSOI technology. First, let me explain how we correlate or derive from the VF-TLP performance measured on a 2-pin device, the potential CDM performance in a chip. We're using the data from the ESD Association Industry Council. What is shown here on this graph is the trend of the CDMP current measured on a 500 volt pre-charged CDM test for various ICs that have different package area sizes, all packaged in BGA type packages. Using this trend line, giving a certain VF-TLP performance, we can extrapolate for a specific package area what the expected CDM performance in terms of pre-charge voltage can be using this clamp if all of the proper CDM guidelines are followed. We will use some of that in the next presentation. But first, let's talk about our SCR-based solutions. An SCR is basically a silicon-controlled rectifier. It is represented by the interconnection of a PNP and an NPN device as shown on the left-hand side. However, we're not talking about plain vanilla SCRs because those plain vanilla straightforward implemented SCRs would probably give you not the proper desired performance. We are talking about highly engineered designs that have various design techniques introduced in the various nodes that are available in an SCR design. So let's have a look at those specialty devices. First of all, we're showing you TLP data. On this graph, they are represented by the full lines. It is from a FinFET technology and 3 voltage domains. So we have here a clamp for 0.8 volt, 1.8 volt, and 3.3 volt. The same clamps have also been measured using VF-TLP, so not 100 nanosecond pulses, but 5 nanosecond pulses. They are represented by the thinner lines here. So what can we see on this graph? If you look at the leakage evolution on the right-hand side, we see that the TLP performance is above 2 amps. We know that it's very well correlated with the HBM performance, so we can deduct here we have at least 3 kilovolt of HBM performance if we can use this clamp properly in an IC design. With regard to CDM or the VF-TLP result, we see slightly above 4.5, at least 4.5 amps of VF-TLP performance. Using the previous graph, this translates into an above 250 volt CDM performance, clamp capability in a 1500 square millimeter BGA package. But let's look at some more data. You see 3 colored curves representing FinFET data for 5 nanometer, 7 nanometer, and 12 nanometer. But more importantly, I'm also showing you dashed lines on the VF-TLP plot. These dashed lines are the so-called overshoot curves. Now, how do we measure them? Well, first of all, let's take a step back and look at how an actual VF-TLP curve is measured. Basically, a TLP stress is applying a square current pulse, and we're measuring that pulse. And then we're also measuring the voltage response of the device. That's the voltage transient. So we want to have one data point of the VF-TLP curve. We apply a certain current level, and then we are measuring the voltage response. We are averaging out the response over the tail, and then that gives us one current value, an average current value, and an average voltage value, and it gives us one dot on the TLP curve. However, there's more information in these curves. If we look at the voltage transient, we see that there is an overshoot in the beginning of the curve. If we are plotting that overshoot value versus the current value, we become the dashed lines. The dashed lines show you that there is a level of overshoot, and it gives you an indication or a qualitative comparison between different designs if you were to compare those. The big question, of course, is this overshoot dramatic, yes or no? To know that, what we do is we build test circuits using the selected clamps and put a parallel victim circuit next to it. in this particular case, a gate oxide. If the gate oxide is not damaged by the test, it means that the clamp has worked effectively and is efficient. We could see that in the leakage evolution of such combined test. For all of the devices shown here, such test has been done, and I can confirm that indeed the gate oxide was properly and adequately protected. Let's have a look at some FDSOI data. Here I'm showing you the test results of two different designs. One is a very effective clamp, it's the blue line, and one is called and considered an ineffective clamp. If we just look at the traditional VF-TLP curves and we look at the leakage evolution as shown on the most right-hand side, we would not see a big difference between the two designs. However, looking at the overshoot curves, we have a much better insight in the operation of these devices. We see a limited shift for the blue line and we see a dramatic shift for the green line. Actually, if we do the test with the parallel victim circuit, we will see that the blue curve is very effective and the green curve is not. Hence, in our designs, the blue curve has been retained as an effective clamp and the green one has been rejected. Well, thank you for listening to this short presentation. If you want to know more about Sofics' robust solutions for ICs, please connect with us over the internet by www.sofics.com or talk to us over email. You can do that at bd@sofics.com. Thank you very much and have a very nice day.